So today we decided to talk about solutions of the Dirac equation and also about the charge conjugation. Now, before I continue, let me ask if you have some questions. I recall that in the last lecture we discussed the concept of Weil spinors, the concept of irreducibility, and we found out that representation of the proper orthochronous Lorentz group on four-dimensional spinors is reducible, so it is decomposable into two irreducible representations, which are realized by means of two-dimensional Weil spinors. We call them dotted and undotted spinors. And we also found out that under parity transformation, one species of Weil spinors, say dotted spinors, go to undotted ones, and vice versa. So from this point of view, these four-component spinors realize irreducible representation of the full Lorentz group, which includes, in addition to proper orthochronous Lorentz transformations, also parity and time reversal. And so especially parity acts non-trivial by mixing, by transforming into each other the Weil spinors. We consider the Dirac equation again. So this is I gamma mu d mu minus mc over h bar acting on psi is equal to 0. And what I will be looking for solutions to this equation, which are given by plane waves, which are described by plane waves. So I take an ansatz for psi on x and t, given by the following formula: an amplitude u, which depends on components of the four momentum p only, and then the standard exponent describing the phase of the plane wave. And so the phase is et, E energy multiplied by time minus P multiplied by X. So that's a usual quantum mechanical plane wave. This wave is called plane because the value of the amplitude U on P depends only on momentum, but it does not depend on X, on the position. And the phase of this wave is one and the same for all points on the same plane. And this plane, this is a plane for which the scalar product P with X remains to be constant. And in fact, this plane is perpendicular to vector P, and P points to the direction of propagation. So P points to the direction of propagation of this wave, to the direction of propagation. So in other words, if you have, say, momentum P pointing in a certain direction, then a plane which is orthogonal to P, to every point on this plane, the phase P multiplied by X is one and the same. And that's why the front of this wave is just a plane. Yeah, you can see this geometrically because you know that every plane is described by the following equation. So X on the plane can be described as some fixed points, say call it x0, plus 2 vectors on the plane multiplied with arbitrary real numbers, say s and t. So let's s and t belongs to R, and say A and B will be 2 independent vectors on the plane. Then this is how any point on the plane is described. And then you see that if you take P with X, where P is a vector orthogonal to the plane, so it means it's orthogonal to vectors A and B, then product P on X, scalar product of P with X, will be just a constant number for all points on the plane. And that's why this plane is called, that's why this wave is called plane. Okay, now we take this ansatz, so ansatz for the solution, ansatz, and plug it into the Dirac equation. And in this way, we get an equation for the amplitude u. Well, you see that these derivatives will act either on t or on x, and correspondingly E and P gets down upon this differentiation, and so equation for the amplitude then takes the following form. Derivative of with respect to time gives energy coming down, minus C gamma I Pi. So this is a term with derivative dxi produce momenta Pi getting down, three-dimensional momenta components Pi getting down, minus mc squared, so a little bit massage this equation, acting on U, on P, is equal to 0. So this is how equation for the amplitude looks like. Now you can recognize that what is written down here is nothing else as a eigenvalue problem for the Dirac-Hamiltonian H. So the Dirac-Hamiltonian H acting on psi is C alpha I Pi plus mc squared multiplied with beta acting on U is equal to E multiplied by U. So this is Dirac-Hamiltonian. Dirac-Hamiltonian. And this is its eigenvalue, which coincides with the energy E. And to come from this form to this form of this equation, all what you need is to multiply the first equation with gamma 0 from the left. And gamma 0 is the same as matrix beta. And in this way, gamma i's will turn into matrices alpha I, and you just get Dirac-Hamiltonian, and then you put the energy to the other side, and then you see that what you get is simply eigenvalue for the energy. So this is very similar to the way you solve Schrödinger equation by means of the plane wave ansatz. You take a time-dependent plane wave, plug into the Schrödinger equation, and then you get eigenvalue problem for the Schrödinger Hamiltonian. Absolutely the same happens here. You just take a plane wave ansatz, time dependent, plug it in the Dirac equation, and then you get a time independent problem, which is an eigenvalue problem for the Dirac Hamiltonian. Okay, so you may look at this eigenvalue problem in components now. So it is convenient to take U and represent it in terms of two-component spinors. So this U is 4-component, but I will split it into phi and chi, like this. Plug into this equation and then use expression for alphas and beta in terms of Pauli matrices. And then equation will take the following form. So it splits into equations for these two-component spinors, which looks as follows: energy minus mc squared multiplied by phi minus C sigma P multiplied with chi is equal to 0. So that's one equation for two-dimensional spinors, and the other one minus C sigma multiplied with P plus E plus MC squared multiplied by chi, and here multiply with phi or acting on phi is equal to 0. Okay, so what you have then is simply a system of 4 homogeneous equations for the components of spinors phi and chi. And in terms of these 2x2 blocks, the corresponding matrix with acting on phi and chi can be written as follows. So E minus MC squared multiplied by identity matrix, which I'm not writing, minus C sigma P here minus C sigma P, and here E plus MC squared. This is a matrix, and this matrix acts on 2 components spinor phi chi, and the result is 0. So this is homogeneous system of algebraic equations, of 4 algebraic equations. For components of the spinors phi and chi. And you know that in order for this system to have a non-trivial solution, it is necessary that the determinant of the matrix which defines this homogeneous system must be equal to 0. Otherwise, there is no non-trivial solution of this system at all. So this means that we have to impose the condition to have a non-trivial solution, namely determinant of this matrix must be equal to 0. This determinant must be equal to 0, and then if we compute this determinant, we see what is this. Explicitly, it is product of these 2 elements minus the product of elements on the off diagonal. And so on the diagonal, you get E squared minus MC squared. And from off diagonal components, you get plus C squared. And if you work out the Pauli matrices, multiply Pauli matrices, what you get here is minus C squared minus C squared P squared. And as we said, this must be equal to 0. So what you see from here is that the condition of vanishing of determinant of this matrix is nothing else as relativistic dispersion relation, or dispersion relation for relativistic particle, which tells us that the energy of our plane wave solution is related to the momentum of this plane wave by the following conditions. So energy is either plus P squared plus C squared plus M squared C4, or it is minus this expression. So energy can be positive and or negative, and it is related to momentum by means of this standard relativistic dispersion relation. Which we also call, in the context of Klein-Gordon equation, the on-shell condition. Is the story with determinant is clear?
Yes, first.
Okay.
Sorry, sir, what was written there? E equals to square root of P squared C squared plus m
p
squared
plus what is written here is actually sorry, this is maybe a bit just a second. I write it once again. I write it once again here to write it more clearly. This is m squared. Actually, c. It's not energy. It's a c in the power 4.
Okay.
C in the power 4. M squared, c in the power 4, and here p squared, c squared. So standard relativistic dispersion relation for a massive particle. And so at this point, of course, you can be surprised that the classical theory, classical Dirac theory, contains solutions with both signs of energy. It has positive solutions and it has negative solutions. So from this point of view, I mean, from classical point of view, the Dirac theory is not well defined because we should not have solutions with negative energy. Energy typically in usual dynamical systems is a quantity which must be restricted from below. And this is not the case here. We can see that we can have, depending on momentum, we can have solutions with any value of negative energy. But we will see that this kind of negative feature or unwanted feature of the classical Dirac theory will turn into advantage of this theory when we come to the quantum world. Meanwhile, we can choose the sign in front of the expression for the energy and produce explicit solution by now specifying this sign. And so once you fix the sign, then say if you fix a positive sign, then you get solution which looks like this. So U plus on P. I denoted U with plus because it corresponds to the positive choice of sign in front of the square root. U plus P is given by phi. And here C sigma P divided by E depending on P plus MC squared. And this is a 2x2 matrix which acts on phi. So solution is given just in terms of two components spin of phi, which remains to be arbitrary, which remains to be unrestricted. Here, once forever, I will fix E on P to be the positive value of the square root. So E on P, I choose to be P squared, C squared plus M squared C4. So sign always will be positive. Once I write E on P, then the sign is assumed to be positive. And this is what I'm having here is therefore solution, positive energy solution of the Dirac equation. Now, if you fix the negative sign in front of the square root, then you get solution U minus depending on P. And then this solution is phi, again, is an arbitrary two component spinor. And here C sigma P divided by minus E on P plus MC squared, and this acts on phi. Where E on P, again, given by the same positive square root. And the fact that I'm dealing with now negative energy is because I put explicitly minus in front of this E on P expression. So this is how explicitly these solutions with positive and negative energy look like. Okay, So this means that since our phi remains arbitrary, we have two solutions with positive energy, and two solutions means two components of phi. Two solutions with positive energy and two solutions with negative energy. And the fact that we have two solutions, this fact hints that there exists another operator which commutes with a Dirac Hamiltonian and which distinguishes between themselves two components of phi. So the fact that phi remains to be arbitrary and unspecified and has two components means that there is another operator which commutes with a Dirac Hamiltonian and which distinguishes between these two components of phi. And this operator indeed can be constructed in an explicit way, and it has a name, helicity operator. Helicity operator. Helicity operator, and constructed as follows. I denote it in this way, this operator, and it's built up in the following way. You need to take modulus of 3 momentum, gamma 5, gamma 0, gamma I, pi, where over index I there is a summation. And this, if you substitute gamma matrices, say in the Dirac representation, then you will find the following answer in terms of Pauli matrices. That this is sigma p, 0, 0, sigma p. And then if you remember our discussion of the transformation law of transformation matrices which realize a representation of the Lorentz group, then you see that here you deal with the operator sigma, the one which we denoted as sigma, multiplied with vector n, where n is a unit vector in the direction of momentum. It's a momentum, in fact, divided by modulus of momentum, and sigma is understood as a 4x4 matrix on the one hand, and on the other hand is a vector built up from 3 Pauli matrices. And this operator sigma we call the spin operator. Spin operator because this object, this matrix sigma, or 3 matrices sigma, better to say, they satisfy the Lie algebra relations for the angular momentum. And this is an operator which we identified with the spin of our particle. And so n here, as I said, it's a unit vector in the direction of the propagation of our wave or particle, whatever you think about it in quantum mechanical terms. You see that the operator which I'm constructing, this helicity operator, is nothing else as a projection of spin on the direction of propagation, on the direction of motion. So helicity is a projection of quantum mechanical spin on the direction of propagation. Okay, now what can be checked is that that this operator is commutes with a Dirac Hamiltonian. So simply if you compute commutator of H with this operator, you find that the result of this commutation is simply 0. So you have two commuting operators. And you know from the course on linear algebra that if you have two commuting operators, you can simultaneously diagonalize them. If one of them at least diagonalizable, then you can simultaneously diagonalize both of them. And this means that these operators will have the same, you can construct the basis in the space, in the Hilbert space, made from eigenstates, common eigenstates of these two commuting operators. So let's say they can be simultaneously diagonalized. Diagonalized simultaneously. Simultaneously. Okay, that's a very interesting fact that we are finding an operator which commutes with the Dirac Hamiltonian, meaning that we can simultaneously diagonalize them. The further properties of this operator are the following: that if you apply it twice, if you compute square of this helicity operator, you find that it squares to 1 to the identity matrix, which means that the eigenvalues of this operator are simply plus minus 1. So let's say eigenvalues of this operator are plus minus 1. Now, thus a state with positive energy can also be an eigenstate of the helicity operator with either positive or negative helicity. And the same, of course, true for states with negative energy. And so if you now take our general solution for states with positive energy and the same general solution, and the general solution for states with negative energy, and further use these states to diagonalize helicity operator on these states, which are already made to be eigenstates of the Hamiltonian, then you find the following very explicit solution for this amplitude U, which is simultaneously an eigenstate of both operators, of H and of helicity. And so somehow to distinguish states with positive and negative helicity, I will use indices 1 and 2. So for instance, if I write U plus, that means I'm writing a solution with positive energy, and 1 as an index up means that I'm considering solution with positive helicity. So helicity has an eigenvalue plus 1. Then such a solution explicitly will take, or can be written with the following in the following way. So first of all, there is a overall normalization which is at your disposal. You can use it for normalizing your spinor in a convenient way. And I will tell what would be a convenient normalization for this case. Of course, the choice of different choices of this normalization do not influence the fact that this U plus 1 will be an eigenstate of H and helicity operator. And then there is a 4-component spinor, which has the following very explicit form in terms of momentum of our wave. So component P3 plus modulus of P, that's the first component. Then P1 plus I P2, the second. The third is C modulus of P multiplied by P3 plus modulus of P. divided by mc squared plus E on P. And finally, the first component is given by similar expression, where you have P1 plus IP2 divided by mc squared plus E on P. So this is how the solution with positive helicity and the positive energy looks like. Do you have any questions here? Is it clear how I got it?
It's clear.
Yeah, so I used my solution for say positive energy, and then I further pick up this phi in such a way that it will also be an eigenstate of the helicity operator, which I have introduced here. So and explicitly in terms of Pauli matrices, that is given by this expression, by this expression here. And you continue this with other. So if you ask about solution with negative helicity but positive energy, you will find the following answer. So this will be again minus P1 minus IP2. The first component, P3 plus modulus of P for the second, and then you have more complicated answer, mc squared plus E on P. And here there will be minus C modulus P, P3 plus modulus P, like this, divided by mc squared plus E on P. And this is what concerns solutions with positive energy and two different helicities. And analogously, you write down solution with negative energy, positive helicity. I do it quickly. Just that this will be in front of you. C modulus P, again here, P3 plus modulus P divided by mc squared plus EP minus minus C modulus P, P1 plus IP2 divided by mc squared plus E on P. And here P3 plus modulus of P divided by, no, there is nothing to divide here. And P1 plus IP2. And the last thing is the U minus 2 on P equals to the following expression. So C modulus P, P1 minus IP2 divided by mc squared plus E. Here, C modulus P, P3 plus modulus P. The same denominator, and finally, this expression here. So what I recommend you to do to check these expressions, you can just put them on Mathematica. Then this becomes really, really very easy. You put on Mathematica gamma matrices, Dirac matrices, so you write down the matrix equation explicitly in terms of these matrices, and then you just also work out what is helicity as a matrix, and then you just diagonalize. And that's the answer you're supposed to find. Where overall normalization can be chosen in a convenient way to provide a convenient orthogonality relations for these four different solutions. And so it turns out then, if you look a bit closer on these findings, then if you choose this normalization in the following way, as mc squared plus E on P. And again, I recall that everywhere here, E on P is a positive root. I'm using only positive root. P squared plus P3 modulus P. Then these solutions are conveniently normalized in the following way. U bar, which is Dirac conjugate spinor with helicity R and positive energy on P, scalar product of this with spinor of helicity S, also with a positive energy, gives simply delta RS. So in other words, the scalar product of Dirac conjugate spinor of positive energy with positive energy spinor of different helicity gives you zero. While U bar U for a positive energy solution of a given helicity gives 1. So very simple normalization. And for negative energy solutions with different helicities, the story is similar, with a little exception that here you cannot reach 1 on the right-hand side, but you have rather -1. But it's a minor thing, so that's a minor thing you have. Okay, so this is how these spinors then are normalized. In fact, you can find also these relations by using the projections, projector operations or projectors on solutions with a definite helicity, simply by using the fact that this helicity squares to 1 to the identity matrix. And so you can introduce helicity plus minus projection operators, which are simply identity plus minus this operator divided by 2. Well, you can see that because of J squared is equal to 1, then J plus minus have all the properties of projectors. And in particular, you can also check that they satisfy the following properties, that if you take J plus minus, so J plus minus is an operator which depends on momentum. These operators which are momentum dependent. And then you see that J plus minus is simply J minus plus, but taken from minus P. Well, this is one of the properties you can verify explicitly from the form of this operator, and that is more or less clear looking at this formula here. Changing the sign of P changes the sign of J, and also in comparison to plus J plus, you will get J minus in that case. Good. This is what we have. In fact, you might think that these solutions we found look pretty, complicated, no, a little bit ugly, because you see there is a certain amount of symmetry broken. You see explicitly these components of momentum entering differently in different elements of the corresponding spinors. But in fact, these formulas immensely simplify if you just go to the rest frame of our massive particle. So if our particle is massive, it has a mass, we can go to the rest frame where P simply is equal to 0. So components of momenta, special momenta are all 0. So we are in the rest frame. So with respect to us, the spinor is at rest. And then you see that these components with positive and negative energy and definite helicity, they simply turn into the matrix standard. Basically, they turn to the standard basis in the space C4. Standard basis in C4. So U plus 1 is 1, 0, 0, 0. U plus 2 becomes 0, 1, 0, 0. U minus 1 is nothing as 0, 0, 1, 0. And finally, U minus 2 becomes 0, 0, 0, 0, 0. So sometimes my pen is not writing for some reason. 0, 0, 1. Okay, so this is what you find in the rest frame. And in fact, you can use this very, very simple expression for components of the spinors in the rest frame to just take this and now do a Lorentz transformation in the arbitrary frame. In the arbitrary Lorentz frame, and then you come back to the result which we have already found. So you just apply Lorentz boost to the particle at rest. You may see, for instance, that this is exactly what is done in the book by Bjorken and Drell. They take this solution, which is a standard basis in C4, in the rest frame, and then transform it with a Lorentz transformation into, well, Lorentz transformation, in fact, Lorentz boost in an arbitrary frame. The only point is that solutions which you obtain in this way do not have a definite helicity upon you perform sort of arbitrary Lorentz boost. Helicity is destroyed, and you need to perform an extra rotation of the spinors to diagonalize the helicity operator by taking linear combinations of two positive energy solutions and separately two negative energy solutions. But in any case, now you understand how it works. So in the rest frame, this answer is extremely simple. Okay, now what we see is that if we consider solutions with positive energy only, then solutions of positive energy but with different helicities are orthogonal. The same is true for solutions with negative helicities. By orthogonality, I mean these equations which we discussed. Now, you can ask yourself what actually happens if you take now solutions with positive and negative energy and take a scalar product of them. So solutions with positive and negative energy. Then here you see that there is a little problem because helicity operator commutes with the matrix gamma 0 that you can understand from the explicit form of this operator. So helicity commutes with matrix gamma 0. Where it is? It is here. So you see you have gamma 5, which anti-commutes with gamma 0, and there are 3 gamma i's, which anti-commutes with gamma 0. Gamma 0 commutes with itself, and so twice minus gives plus. And so indeed, helicity operator does commute with gamma 0. And why gamma 0 is important? Because gamma 0 we use to define the Dirac conjugate spinor. So I recall that Dirac conjugate spinor is simply U dagger, usual Hermitian conjugate spinor, and then multiply with gamma 0. This is what is called Dirac conjugate spinor. And you remember why we are interested not in just Hermitian conjugate spinors, but in the Dirac conjugate spinors, because Dirac conjugate spinors transform in the same way under Lorentz transformation. No, not in the same way. They are transformed under Lorentz transformations with the inverse matrix of Lorentz transformation in comparison to the matrix of under which the spinor U transforms. And so that was useful because then we can easily build up the Lorentz covariant combinations. For instance, U bar U is a scalar, U bar gamma mu U is a vector, and so on. So that was very useful for constructing objects with well-defined transformation properties under Lorentz transformations. That's why we like this Dirac conjugate spinor. Now, with respect to helicity, everything is fine. So helicity goes through gamma 0 and act on the U itself because helicity commutes with gamma 0. But this is not the case for the Hamiltonian H. For the Hamiltonian H, you don't have such a nice property. For the Hamiltonian H, H does not commute with gamma 0. And that means that if you take this leads to the fact that if you take now two spinors of different energy, then the scalar product will not be 0 as you want, because taking scalar product of positive and negative energy solutions would normally you think gives you 0, but it's not, because Hamiltonian does not commute with gamma 0. Gamma 0 enters the definition of the conjugate, Dirac conjugate spinor. Rather, the exact relation between H and gamma 0 is as follows. So if you take gamma 0 and then H, depending on momentum P, gamma 0, then the result will be H on minus P. So gamma 0 turns the sign of momentum in the Hamiltonian. And that is, of course, clear, very much clear from the definition of H. So H on P is C alpha I pi plus mc squared beta. And alpha I, they are simply given by gamma 0, gamma I. But gamma 0, when we will be commuting H through gamma 0, gamma 0 through H, then we see that gamma 0, of course, commutes with gamma 0, but it will meet gamma I with which it anti-commutes. And beta is again gamma 0, so gamma 0 will commute with it. And since it's anti-commute with gamma 0, it will lead to the change of the sign in front of this combination alpha I pi, which you can restore back by changing the sign of momentum. And therefore, the behavior of the Hamiltonian under sandwiching in between gamma 0 is of this type. Sign of momentum is changing in H. And in fact, you can use now this property in the following way. So first of all, you see that if you take a solution with a positive energy and apply to it the Hamiltonian, depending on momentum P, you get, of course, eigenvalue, which is a positive eigenvalue, E on P, multiplied by U plus on P. Then, from here, follows the following. If you take a Hermitian conjugate of this equation, since the Hamiltonian is Hermitian, you get U dagger on P H on P equals to energy is real, so nothing happens to it. U plus you get U.
Professor.
Yeah.
So here,
Dega.
are we working in any particular basis here?
Where? This is not so much important. Particular basis plays no role here. I'm just using the Clifford algebra relations, which are the same in any basis.
So h gamma 0 is not equal to 0 in both bases.
In any basis is never equal to 0. Gamma 0 cannot be 0. Gamma 0 is never 0.
No, commutation of h gamma 0.
H gamma 0 is in any basis. This is not 0. And in any basis, you have this relation here. In any basis. It does not depend. This relation here does not depend on the basis. It's simply a result of the fact that gamma 0 anti-commutes with gamma I. And this is simply the relation of the Clifford algebra. Regardless of how you realize this, with which matrices you realize this relation. It's in any basis, this is a fact. So basis is playing no role here.
Okay.
You just use Clifford algebra. You see that from this Clifford algebra relation, it follows that gamma 0 anti-commutes with gamma I, because you can rewrite it in this way. So gamma 0 gamma I is minus gamma I gamma 0. Therefore, gamma 0 anti-commutes. So there appears then minus sign when you will be anti-commuting gamma 0 through, commuting gamma 0 through H, there will appear minus sign here. But this minus sign use an attribute to the momentum Pi, and then this relation here follows. Now, once again, so you take a positive energy spinor, apply to it the Dirac Hamiltonian, you get eigen value E on P, which is real. And then if you perform the standard Hermitian conjugation of this equation, then you get Hermitian conjugate spinor. So this is Dega up means Hermitian conjugate. And the Hamiltonian is Hermitian, so it just goes to the right, and energy is real. So this is what you get. Now, consider U Dega plus. So U Dega plus on P contains gamma 0. Now, you can compensate this gamma 0 by putting extra gamma 0 and then putting H on P and then gamma 0 back. So I consider such a combination. U plus bar, gamma 0, H, gamma 0. And then what we have here is simply the following thing. So this is U bar plus is E on P, multiply with E bar plus on P. E bar plus on P, because what is written down here is simply the same relation as I have here. What I have done, I just plug in gamma 0 squared inside. Then I multiplied this from the right by gamma 0. This becomes U plus bar on P. And on the left-hand side, you get what I'm writing here. So this is direct consequence of this Hermitian conjugate relation. It looks like this. On the other hand, we know now that what is written down here is H on minus P. On H on minus P. And therefore, Therefore, what I have is U plus U bar plus U bar plus on P, H on minus P equals to E on P, U bar plus on P. Okay, good. And in this relation, what I will do, I will just multiply it from the right with spinor U minus on minus P. And I will tell you in a moment why I am doing this. So what you get is U plus bar on P, H on minus P, acting on U minus on minus P, equals to E on P, U bar dega on P, U minus on minus P. This is nothing else as U minus on minus P, because what is happening here is that the Hamiltonian is applied to a solution, to an eigenstate, to its eigenstate with a negative energy, and therefore what you are supposed to get here is the same eigenstate multiplied with an eigenvalue, and eigenvalue is a negative value of energy. So it is minus E on P, where E on P, I recall, it is positive. It is taken as a positive root. Therefore, what I'm finding here is a contradiction in a sense that I'm getting an equation minus E on P, U bar dega on P multiplied with U minus on minus P equals to E on P, the same thing, but with an opposite sign. From where you can conclude only one thing, that for this to be true, the only way to get out is to conclude that U bar plus on P and U minus on minus P actually equals to 0. This means that these solutions, U plus bar and U minus on minus P, they carry different sign of energy. So one is energy plus, another is energy minus. And moreover, they are orthogonal to each other. And we see this orthogonality, we prove, in fact, this orthogonality by using this consideration as I have done. And this is what should be taken as an orthogonality condition of positive negative solution, because if you would do the pairing of solutions with the same momentum, then you will find that it is not 0, exactly for the reason which I mentioned, that gamma 0 does not commute with the Hamiltonian. Although if you change the sign, as we have here, of solution with negative energy, then the result is 0. So this consideration suggests that it is convenient to introduce a spinor V, V minus with a helicity S, which should be taken as, or should be defined, V minus S, which should be defined simply as U S minus, U S minus on minus P. US minus on minus P. And then the full set of the orthogonality conditions, which you deduce from these relations, is the following. U bar R plus on P, U plus S on P is delta RS. So this is as before, nothing changed here. Then you can also check that with minuses, with these, which correspond to negative energy solutions. Also, these solutions are orthogonal for different helicities, but with a minus sign as before. As was before. So minus delta RS. And finally, now the result of our consideration here is that we have now V bar R minus on P and U plus S on P gives us 0 for any R and S. And analogously, what we have is U bar R plus on P with V minus S on P also gives 0. So this is the orthogonality conditions. Now the full set of orthogonality conditions among our spinors. So think a minute about it. This is what we have.
So we need to consider orthogonality between U bar and U, where we just consider the orthogonality of U plus and U minus like this.
Yes, so instead of U minus disappear from this discussion. You see there is no U minus. Instead of U minus, what is introduced is V. And V is U minus on minus P. And then for this new V's, orthogonality conditions for solutions with positive and negative energy look like indeed they are orthogonal. V is orthogonal to U for any helicity. So V essentially is the same as U, but taken with a minus P. This allows you to write this solution having the same momentum in this V and U, but you have different letters. In one case you have U, in the other case you have V. But there is no, I mean, once you introduce V, you can forget about U minus. In principle,
Yes.
you can also forget about lower signs plus and minus, because now U is only positive energy solution, and V is always negative energy solution. So in principle, you can forget about plus minuses below. But I will keep them just to remind the explicit sign of energy. They remind you on their origin of having explicit sign of energy. But in principle, you can get rid of this plus minus. Just have U and V. U positive energy, V negative energy, and then U bar with U, V bar with U is orthogonal, and U bar with V is also orthogonal.
Actually, I'm a little bit lost. Why we introduced the complex conjugate U bar? Because in the beginning we only have U plus and U minus. Why we need a complex conjugate?
Yeah, that's exactly what I mentioned. U bar is U dega multiplied by gamma 0, and this is conjugate Dirac conjugate spinor. Dirac conjugate spinor, which we introduce in order to build up a well-defined bilinear combinations which have good, well-defined transformation properties under Lorentz transformations, because the spinor U bar transforms under Lorentz transformations in a nice way. So if your spinor U transform under Lorentz transformation as U goes to SU, then U bar transforms as U bar multiplied by S minus 1 from the right. Okay? And then from here, you see, for instance, that combination U bar U, which is a scalar product of a row with a column, is simply a Lorentz scalar. A scalar under Lorentz transformations. U bar gamma mu U will be a vector, and so on. So you have well-defined combinations with well-defined transformation properties under Lorentz transformations. That's why in this theory, people always consider Dirac conjugate spinor, U bar, instead of the usual Hermitian conjugate spinor.
Okay.
That's the reason. That's the reason why people use this U bar and introduce and work with it. It's better object than just U itself, U dagger itself. So it's just U dagger multiplied with gamma 0, and gamma 0 helps to have this nice transformation property that U bar transforms just with S minus 1. Otherwise, U dagger will transform with S dagger, and S dagger is not the same, is not always the same as S minus 1. It is the same if S is a rotation, but it's not the same if S is a Lorentz boost. If you come back to our discussion of Lorentz transformation, then you see that this is exactly what we have discussed there. Okay, well, you see, for helicity, we have introduced two projections which project on states with positive and negative helicity, where in fact you can do the same also for projections on solutions with positive and negative energy. So this is convenient if you have an arbitrary spinor. You can decompose it then into solutions of positive and negative energy by using the projectors. One projector projects on solution with positive energy, and the other will project on solutions with negative energy. And these projections are explicitly constructed as follows. So MC identity plus P slashed divided by 2MC. And here this is constructed similarly, MC identity minus P slashed divided by 2MC. This is how projectors on positive and negative energy are constructed. And if you write down explicitly this P slash, which is P mu gamma mu, then this will look as follows. Gamma 0 E on P, this square root, minus C gamma I P I plus MC squared multiply with 1 divided by 2MC squared. And analogously here is minus gamma 0 E on P minus C gamma IPI minus MC squared multiply with identity divided by 2MC squared. And these projectors, lambda plus, lambda minus, well, first of all, they are projectors, which means that the following relations are satisfied. So lambda plus squared is lambda plus, which means that lambda plus is a projector. Lambda minus squared is equal to lambda minus, so lambda minus is also projector. Then these projectors are orthogonal, which means lambda plus lambda minus is equal to 0. No, and finally, you see that lambda plus plus lambda minus is equal to an identity, one that you immediately see by adding up these two. So they provide decomposition of identity. They provide decomposition of identity. And now you can also check that lambda plus, if you apply it to our spinors u plus 1, 2, you will get u plus 1, 2. So it's solutions with respect to this lambda plus, u plus eigenstates with eigenvalue 1, and lambda minus acting on v minus 1, 2. For this lambda minus, this v minus eigenstates with eigenvalue 1. So v plus and v minus form a basis, and in the full space, space of solutions, and these are separately eigenstates for this project. I mean, for they are lying in the subspaces which are defined by means of this projectors lambda plus and lambda minus. And there are also important formulas which people often use, namely this lambda plus and lambda minus. They can be expressed in the components of this spinors u plus and u minus. So in particular, lambda plus is a 4x4 matrix, and if you ask explicitly about its matrix elements I and j, then this can be written in the following way. You have sum, say R is equal to 1 and 2, so sum over all helicities, all two helicities, u plus R with index I, and u dega R plus with index j. So we know that u plus R is a column for which we have an explicit form, and we take i's component of it, and u bar is a row for which we also have an explicit form, and then we take its j component, and then it produces us a matrix. If we run through all I and j, then we have all matrix elements of matrix lambda plus. No, and if you wish, if you want to write it via u plus minus, and this is gamma 0, if you write it explicitly, then this is the same as R from 1 to 2, u R plus I, u R plus dagger here, gamma 0 j. And also we can have lambda minus ij. So it's similarly, it's constructed via components v, and so R is 1 to 2, v R minus with index I, v R bar minus with index j. And if you wish, this is also can be written as sum from 1 to 2, v R minus I, and then v minus R dagger gamma 0 with index j, like this. That is basically all, which now allows us to write down the general solution of the Dirac equation, or basically a decomposition of the Dirac spinor via the basis of plane waves. So if I now take a superposition of solutions we found, I will get a general solution of the Dirac equation. So plane waves actually provide the basis over which I can expand an arbitrary solution. And this means that here I simply implement now a superposition principle, because Dirac equation is a linear equation. So if I have two solutions, then the sum of these two solutions is another solution of this equation. And so if you want to construct an arbitrary solution, then you simply take sum of all solutions, which means that we are taking an integral with a certain integration measure, convenient integration measure implied by our normalization of spinors. And then this is in the power 1/2. And then this is constructed in the following way. Sum over two possible helicities, so from 1 and 2. Then there are coefficients BR on P, amplitudes, let's call them amplitudes. Solutions spinors with positive energy, U plus R, depending on P, and then the plane wave, minus I over H bar, which I write now in the concise way as P mu X mu, plus the coefficient of V minus solution with negative energy and helicity R. I will denote dr with star. It's more convenient for me to use here dr with star on P. And this is multiplied with I over H bar. And I have to change the sign of momentum, which results upon the change of variables with the fact that I will have here a positive exponent P mu X mu I over H bar. Okay, so this is a general solution of the Dirac equation as a superposition of plane wave solutions we found. And we use the fact that this U plus R and V minus R form a basis in the space of solutions. They form basis. So this is a basis elements. And then for each momentum P, we have the corresponding spinors. Then we take this solution, multiply it with arbitrary coefficients, which I denote as BR on P and dr star on P. And then I integrate over all possible values of P. And what you see, what is in front of you, is a general solution of the Dirac equation.
Can't we write dr star as br star?
Sorry?
Can't we write dr star as br star?
No, that's something which we cannot do here in this case. So spinor psi remains a complex object. So its components are complex. And amplitudes BR and dr star, they are completely independent. They are not related by any relation.
Are we still in scalar field or complex?
No. We are in the Dirac situation. So psi is a 4-component spinor, and components of this spinor are complex.
Okay.
They are complex. So here U plus on P and V minus R on P, these are particular spinors which we have constructed at the beginning of this lecture. This is these guys here, about which we know that they are solutions of the Dirac equation with a definite energy and definite helicity. Then instead of U, we introduced V to guarantee better orthogonality relations between positive and negative solutions. And after that, the statement is that any solution of the Dirac equation can be expanded over the basis of this solution we found with a definite momentum. Because the plane wave is a solution which carries definite momentum. So momentum is also a basis label, right? We fix it, and then we have a solution. Now, what I'm saying is that we have to take this solution, regard U plus R and V minus R as a basis elements. We multiply these basis elements by arbitrary complex coefficients, because psi on X is a complex spinor. Then we sum up over all helicities and we integrate over all P's. And then we have a general solution of the Dirac equation. Very similar to the general solution of the Klein-Gordon equation we found at the beginning of our course. Now, there is no mystery at all in what we have found. You can check by direct calculation that this is a solution of the Dirac equation. All what you need to do is just to take the Dirac operator, I gamma 0 d over dt, c dt, plus I gamma I d over dxi, minus mc over h bar. You need to take this Dirac operator, and act with it on psi x. And so when you act on psi x, this essentially means that you get it under the integral and act on the exponent, right? Because it's an exponent which depends on x's over which you differentiate. So you take it inside, and therefore you act on minus IH bar. Say, for instance, in the case of the first exponent, there will be ET minus PX. And when you act on it, you will see that what you will get is gamma 0 divided by CH bar. I'll take something out. E on P minus H on P, Dirac Hamiltonian, acting on exponential minus I over H bar, ET minus PX. And then you remember that, for instance, in this case, you have also U plus on R. So this amplitude is multiplied by U plus R. So U plus R is standing then here. And U plus R is a positive energy solution of the Dirac equation with eigenvalue EP. And so this is nothing else as 0, and therefore the result is 0. So when you will be acting with a Dirac operator on psi x, this term under this operator turns to be 0. And analogously with this one, when you act with the Dirac operator inside this integral, this term under the action of this operator turns to 0, regardless of what these numbers BR and D star R you have chosen. So for arbitrary amplitudes BR and DR star, you will have a solution of the Dirac equation. Now, maybe I should not hide from you the fact that in the quantum theory, the operator BR will become an operator of annihilation of electron, So this is amplitude will receive the meaning of the amplitude or simply annihilation operator of electron, while these R star will turn into the operator of creation of positron. So this is how these amplitudes of classical theory will be reinterpreted in the quantum theory. Again, this situation is very similar to what we have, say, for the real scalar field and more generally for a complex scalar field. So this situation which we have here more reminds the situation with a complex scalar field, when we have a complex amplitudes A and A dagger, and A and B dagger, in fact. And in the real case, indeed, instead of D star R, I should write BR star. But since we are now in the complex situation, then these amplitudes are not related to each other. we do not impose any reality condition on psi on x.
So, for example, if I say that the instead of dr star, if it's, for example, if it's br star, so will the probability of finding will the probability density of finding a positron and finding an electron will be the same?
No. You have to be careful here. So far we are considering classical theory. In the quantum theory, Br and D star R will become operators. And this will be different operators. You cannot say that one operator is equal to the other. This is not what you can say, because the interpretation of these operators will be that these operators create or annihilate different types of particles. Different. You cannot say that one operator is equal to the other, because it makes no sense in the quantum theory.
No, and then that is star or yes, star and same.
Yeah, and they simply different. And again, if you want to describe all variety of classical solutions, you should not impose any relation on Br and Dr star. If you assume any relation between them, then you will be missing a part of the solution space. You see? So arbitrary amplitudes, Br and Dr star, are allowed here. Arbitrary numbers. Then you will be describing a general solution of this equation.
Yes, I understood. But like, for example, if we calculate xi star x, and then we multiply for finding the probability density.
Yeah.
So here Br, and if it's not Dr star, if it was Br star, so
well, you see, in the classical theory,
equal.
I can tell you what these are. So in the classical theory, if you don't go to quantum theory, then these amplitudes simply describe how much of the negative energy solutions are present in comparison to the positive energy solutions. So these two terms have a very different interpretations, because terms with Br contribute positively to the energy. Terms with Dr star contribute negative to the energy. They are very different from this point of view. If you want, for instance, to have solutions with zero energy, you might think you can try to arrange Br and D star R in such a way that you would get a solution with zero energy. For instance, if you want solution with definite value of energy, then you can pick up these Brs and Drs in a certain way, certainly. But then you will get a particular solution with a certain energy. Now, what I'm saying here is a general solution. General solution allows you for arbitrary Br and Dr star. And again, the point is that in one case, Brs represent the contribution of positive energy solutions, and D star are responsible for contribution of the negative energy solution into the general solution of psi on x. So U plus and V minus are special solutions which we pick up as basis elements. And then on these solutions, we span all linear combinations. And linear combinations include here also integration over momentum, because momentum is also a label of our solution. And we are taking this span with arbitrary coefficients to have arbitrary linear combinations, and the coefficients of these linear combinations are exactly what we call Br and Dr star.
We have to take momentum here, right? Because we are working in the momentum space.
We work in the momentum space, and momentum is like also a label of one particular solution. Each particular solution corresponds to each particular wave. It contributes with a particular wave having a particular momentum. Now, taking superposition of all these waves, in other words, taking this integral over all momentum, we describe in this way all possible linear combinations of our solutions. And in this way, we get a general solution, indeed. Okay. So it's very similar to what we have done when we were talking about general solution of the Klein-Gordon equation. Then we found the amplitudes A and A star. There were only A and A star because in that case, we were talking about a real scalar field. That's the difference. If you would talk about complex scalar field, we will find two independent amplitudes, A and B, or A and B star, if you wish. And here we are working not even with just complex scalar field, but we are working with a spinor field. And as you see, spinor field must have 4 complex components. And indeed, it has 2 components which are described by BR, like independent coefficients, R taking values 1 and 2, and the other 2 independent complex components are related to dr star, because psion x has arbitrary 4 complex components, and that's exactly what is taken on the right-hand side now by BR and dr star. You see? 4 complex components on the left here, and 4 complex components on the right, which are now these 2 complex numbers and these 2 complex numbers.
Yes.
So in this way, we reproduce, and moreover, what is written on the right solves the Dirac equation. So it's a general solution of the Dirac equation. And it represented in the nice form over decomposition over the basis of, as a decomposition over the basis of plane wave solutions with positive negative energy and with positive and negative helicity. Okay, one more comment I have to give here is the following. Let me say the following, that for a massive particle, the helicity operator does not commute with Lorentz transformations. I mean, so far we're talking about helicity and the Hamiltonian. But in principle, what is also in the game are Lorentz transformations. Now, under arbitrary Lorentz transformations, neither Hamiltonian nor helicity operators are preserved. Even with respect to their usual rotations, you have the following transformation properties. So the Dirac Hamiltonian transforms as follows. So if I take a Lorentz transformation S minus 1 depending on the rotation matrix R and apply to the Dirac Hamiltonian this Lorentz transformation S minus 1 R H S on R, then the result of this will be H with a transformed momentum R acting on momentum P. This is, of course, related to the fact that H is a matrix. It's not a scalar object. It's a matrix. And S on R is also a 4x4 matrix. And this is a way how it acts on the Hamiltonian H. So this means that when you transform a Lorentz frame by means of Lorentz transformation, in general, your Hamiltonian undergoes a transformation. Particularly, it is the Hamiltonian evaluated at the transform value of momentum P. Similarly, if you take helicity, it transforms also under these transformations, Lorentz transformations, in a similar way. It is a helicity with a momentum transformed by the 3x3 matrix, say, of rotation. And so in the case of the Klein-Gordon field, there was a difference. So invariance, the Hamiltonian was invariant with respect to such transformations because the Hamiltonian in that case depends on p squared, and p is a vector which length is invariant under rotations, right? So if you take a vector and rotate it, by the definition of the rotation group, the length of this vector must be preserved. Now the Dirac Hamiltonian is different. The Dirac Hamiltonian involves momentum not like a p squared, but involves it as gamma I pi, and it's a big difference. Now under rotations, by Lorentz transformations, result is that you have Hamiltonian at rotated momentum p, and this is a different Hamiltonian in general. You see, the only thing which preserves actually the Hamiltonian and also helicity are rotations which happen in the plane orthogonal to momentum. So if the momentum is looking in one direction of our particles, say p, then if I take a plane orthogonal to this momentum and rotate around it, around the direction of p in this plane, then this will be invariant, momentum p will be invariant, and here it's also will be p. So in this case, under these restricted rotations, neither Hamiltonian nor helicity will be changed.
Professor?
Yeah?
With respect to Hamiltonian, so this equation shows that Hamiltonian is invariant under a rotation transformation.
It is invariant only if you perform rotations in the plane which is orthogonal to the momentum p. In general, it is not invariant. And the same is with helicity.
Yes.
And this is, I mean, this, you should not be surprised to this because, I mean, in general, when you introduce the concept of the Hamiltonian, you always break Lorentz symmetry. In any case, you break it. Because, for instance, you cannot anymore consider Lorentz boosts because the Hamiltonian defines an evolution in a definite time direction. So time direction is fixed. So your Hamiltonian defines an evolution with respect to the fixed time direction. And when you perform Lorentz transformations, which mix time with space, this means that in fact now you give a time a new direction, and your old Hamiltonian then is not valid anymore. The Hamiltonian formalism, which you constructed with the old Hamiltonian, is not anymore valid. So passing to the Hamiltonian formalism always breaks Lorentz symmetry, at least with respect to the boosts. Yeah?
Yes, but we think if we're only considering spatial rotations, Hamiltonian should not change.
Well, here, if you do this for the case of Klein-Gordon field, then the Hamiltonian is not changed. But here the situation is different because you have a Dirac equation. And the Dirac Hamiltonian, which is a matrix.
And what does this mean? It means that if we change change the observation angle and the energy of the particle changes.
Yes, of course, because you're rotating yourself with respect to, well, okay. So what we are talking here is, of course, what is called first quantized Hamiltonian. This is not the actual Hamiltonian of the quantum theory. Okay? This would be something which we discuss, remember, when we were talking about the difference between first quantization and second quantization. So here we are trying to interpret, no, not trying, but here we look at psi as a solution of a Schrödinger-like equation, which we call Dirac equation. Okay, so this is what we are talking about here, is therefore like a first quantized approach where we try to treat psi as a, say, wave function of a single particle, and therefore psi and therefore H here is understood as a Hamiltonian of a single particle. And the Hamiltonian of this first quantized theory, as you see, it does not depend on the modulus of the p squared, but rather it depends on the components of p themselves. And this makes a big difference with the usual situation, with the usual, say, Klein-Gordon field. Because now rotating, performing a transformation to a different frame, rotating, means also that the energy changes. In a sense of changing the value of momentum. And the Hamiltonian depends on the components of P rather than but you have to be careful here. I mean, okay, this is not the point which I wanted to make to make it. The point which I want to make is the following. I want actually to concentrate more on helicity. The Hamiltonian is something which also breaks even under Lorentz boosts. And here the situation is with helicity is actually more dramatic, because helicity depends on the Lorentz frame. So in other words, what you call a state with a positive helicity in a different Lorentz frame can become a state with a negative helicity. You see? So helicity is not a Lorentz invariant quantity for a massive particle. If particle is massive, then helicity is not a good observable for a massive particle, because it depends on the choice of the Lorentz frame.
Yes.
But for massless particle, for massless case, the situation is different. And this is due to the massless Dirac equation. Because if you write the Dirac equation for the massless particle, then there is no this mc squared term in the Dirac equation. And the Dirac equation takes the massless Dirac equation takes the following form. So gamma I pi is equal to E over C gamma 0. So in the momentum space, say for a plane wave, this is how the massless Dirac equation looks like. And for massless equation, we know that energy is given by plus minus C modulus of P, right? This is a formula which we will get from this general formula, P squared C squared plus M squared C4, if the mass turns to 0, right? If mass turns to 0, then we get energy to be equal to plus minus C modulus of P. This means that if you now look at the operator of helicity, you see that in general, this is 1 divided by modulus P, gamma 5, gamma 0, gamma I, P, I. And because of this relation here, you see that this is plus minus, I substitute energy. So instead of this gamma IPI, I use this expression here. So I get plus minus C modulus of P divided by modulus of P. So modulus of P will cancel. I get gamma 5, gamma 5, gamma 0, gamma 0. That's upon substituting this expression due to the massless Dirac equation. Gamma 0 squared is 1, and therefore I'm left with essentially with what? This E over C also cancel. There is no C in this formula. So the answer is plus minus gamma 5. So for massless particle, chirality, helicity operator is the same as chirality operator, gamma 5. Remember, last time we introduced Weil spinors with respect to behavior of these two component objects with respect to gamma 5. And so helicity for a massless, in the massless case, is not distinguished from chirality. Helicity and chirality become the same, and they become an absolute thing, which does not depend on the frame, on the Lorentz frame. And this is also something obvious because in the Lorentz frame, for a massless particle, you don't have a rest frame. Basically, your particle is moving with the speed of light. And since you're a massive person, you can never reach it. You can never sit on it. You can never catch it. And since you can never catch it, you can never go to the rest frame of this particle. Well, for a massive particle, if your speed is, if your momentum is high enough, you can catch it, you can sit on it. And in this system even, and you can go even faster than it. And if you can go faster than it, then with respect to you as an observer, the sign of momentum will change. So you can change the helicity because you changing your frame, you can change the sign of P. And if you change the sign of P so easily, you change the helicity, right?
Yes.
So your particle is slow, it's massive, it goes slow, then you go faster than it, and then you see on it from your frame, and then with respect to you, the particle will change this sign of momentum. If it will change the sign of momentum, it will change its helicity. So helicity in this case is not absolute quantity. If it was +1, you can find a frame where it's -1 if your particle is massive. If it is massless, this is not possible to do because you can never reach it. And then chirality becomes an absolute quantity. And that's why our neutrinos are, as people say, left-handed. They have a direction of momentum coincident with the direction of spin. And so for them, helicity is +1. While for antineutrino, the situation is opposite. Momentum is going opposite to sigma in a way, and helicity is -1. And so that's why antineutrino are, as people say, right-handed. So chirality, right-handed. Left-handed means particles of different chirality.
We haven't found it yet.
Hmm?
But we haven't found it yet, right?
Yeah. Okay, so that is what I wanted to tell you today.
Professor,
Yeah.
like if I'm moving for a massive particle, if I'm moving with its direction of motion, so if I overtake the particle, so my chirality will get, the sign will get reversed, right?
Yeah, that's
So
right.
right now if I am not moving straight, if I'm moving at an angle theta, so what will happen to its eigenvalue? It should not be +-1, or it should be like depending on some angle.
Yes, that's because as I say, from these formulas, you clearly see that chirality, sorry, not helicity and the Hamiltonian do not even commute with rotations. So if you rotate yourself in a different frame, then you lose the notion of helicity in a sense that you have a state with no definite helicity. Helicity is destroyed. You need, in the new basis, you need again rediagonalize your spinor with respect to the chirality operator. No, because You have your spinor, say u plus or minus, does not matter. Then you perform Lorentz transformation. Then the guy changed. In the new frame, it's already SU. And then you see that if you apply chirality, then this will not be equal to SU plus anymore. You see, once you are talking about the Hamiltonian and the helicity operator, things are okay. But that means that you fix a Lorentz frame in which you write your Hamiltonian and your helicity operator. Then in this frame, you can diagonalize them and you have a nice basis, positive energy solutions, and also definite helicity, plus or minus. Now, if you perform the Lorentz transformation, then this nice property gets destroyed. And you have to re-diagonalize again. So solution basically mix, different chiralities mix.
Or can we add some extra terms to it that doesn't commute?
That I don't quite understand what you mean by this. I mean, you just change a frame, you get a new spinor, because spinor transforms. So in the new frame, it is SU. And now, since chirality does not commute with U, which this formula shows you exactly that it does not, if you put S on the right-hand side, then this is how the commutator looks like. Chirality S, and then chirality, sorry, not helicity. Helicity S, helicity, but helicity on the rotated momentum, and then again S. And then you see that this will be again P if you rotate in the plane orthogonal to P. Only in this case, only under this particular restricted transformations, your helicity will not be changed. But only if you perform any other transformations, your helicity will be changed.
Yes, depending on the angle.
It depends, yes, it depends, yeah, sure. Because this is a Lorentz transformation does depend on how you do it.
Is it like we are working in a pure boost condition?
I did not discuss boosts here, but boosts are even more dramatic. Boosts completely destroy everything. Boosts in first turn destroy the direction of time, they destroy the Hamiltonian and so on. But here is even, how to say, a subgroup of Lorentz transformations, which is made of rotations. So rotations, I'm considering only rotations. And already with respect to rotations, there is no invariance of this quantity for massive particle as helicity. In fact, helicity operator is not the only operator which commutes with the Dirac Hamiltonian. Another operator which commutes with the Dirac Hamiltonian is the total momentum. Total momentum is an integral of motion. So total momentum, Ji, the total momentum is given by epsilon ijk. If you use Noether's theorem to compute it, then this is the way how it will look like. Xj pk, where pk is the component of momentum, plus h bar. So this is orbital part, but there will be also spin part, which is exactly given by this sigma I. And you can check that h also commutes with ji, so the result is 0.
Total momentum should also consist angular momentum. No.
Yes, it consists of two parts. For Dirac particle, it consists from an orbital part, and this is this piece here, and it consists also from spin part. because it's total momentum, it's sum of two. And what is interesting that for a massive relativistic particle, neither orbital momentum nor spin are separately conserved. And this can be traced back to the fact that for the Dirac field, the stress energy tensor is not symmetric. And that's why, as a consequence, for a moving particle, only projection of spin on a given direction kind of has a definite value. Helicity, only helicity has a definite value. Projection of spin on the direction of momentum, and that is what is conserved.
Yes,
What
sir,
I mean is that if you try to separate, if you take separately this piece, it will not be a conserved quantity. If you take separately this guy, it will not also be conserved quantity. What is conserved, either this sum of two or helicity, which is if you denote this as sigma, then what is conserved is sigma multiplied by p divided by modulus of p. This is what is conserved, and this is our helicity. Okay, so this is conserved in the sense that it commutes with the Hamiltonian. Commutes with Hamiltonian. And the total momentum also commutes with the Hamiltonian. Because it's total momentum, it comes from the Noether's theorem. It's total momentum, it's you derive it with respect to rotations, three-dimensional rotation, then you use Noether's theorem, and this is the expression which you derive. So that's a good exercise, actually, to derive this formula which I'm presenting here. But you will find two terms, not one. The orbital part and the spin part. And if your particle is relativistic, so it moves sufficiently fast, close, say, to the speed of light, then you cannot really distinguish between what is orbital here and what is spin. Of course, you may know what is spin, because if it's still massive, you can still go to the frame where p is equal to 0. But again, this is a choice of the Lorentz frame. If you can sit on it, then with respect to you, particles will not be orbiting, which means that you kill orbital part, and then you have a chance to see the spin part, measure spin part, if you sit on your particle. But if your particle is massless, then there is no way you can actually, sit on it.
But total momentum should also consist of linear momentum, right? Which doesn't commute with.
What do you mean by linear momentum?
Linear momentum also, right? If the particle is moving in a direction linearly.
I think it means just the momentum of the particle, the p.
Just the momentum of the particle. Yes. Particle momentum is conserved. Yes. Particle momentum is conserved. And particle momentum is conserved. That's why we are allowed to talk about eigenvalues of the momentum. Absolutely. Yeah, sure. Of course. That's why I'm talking here all the time about eigenvalues of momentum operator, which has these components p, which I'm writing as numbers. That's the reason, I mean, that's why they are conserved. Or better to say, I'm doing that because total momentum, not total, linear momentum is conserved. Usual momentum is conserved. Momentum, which is coming from the homogeneity of space, that I can make shifts in space. That momentum is conserved, no problem. But if you take a combination epsilon ijk xj coordinate with the momentum pk, and try to see if this commutes with the Dirac Hamiltonian, you will find that the result is not 0. This will not be 0.
Yeah,
but
only the
if you
combination.
Yes, but if you take a combination with this additional sigma term, sigma I terms, then you will find 0. And from Noether's theorem, you also find these two terms, but not only one term.
So the Hamiltonian is not invariant under rotation, and helicity is not invariant
Yes,
in rotation.
yes,
So
yes, yes.
do we have something that is invariant in rotation for this spinner?
Yes, of course. I mean, you mean by if you want to characterize invariance, then you need to characterize invariance of the Lorentz group. And invariance representation of the Lorentz group, they are given by mass of a particle and the spin of the particle, which is eigenvalues of the so-called Pauli of the second Casimir of the Poincaré group, built out of so-called Pauli-Lubansky vector.
So we only have
that's why we have scalar particle, spinor particle, vector particle. These are all different representations of the Poincaré group and Lorentz group in particular.
Okay, so for spinors, only invariant character is mass and spin.
Mass and spin. And that's why we are talking here about particles of spin 1/2, because they carry a definite representation. We know that we can characterize them by a definite representation of the Poincaré group, and the number which we associate to this representation is spin. And in this case, we know that the spin must be 1/2. We associate a definite spin to this representation of the full Lorentz group.
Okay, I see.
But once again, you should not be surprised that the Hamiltonian formalism is always break Lorentz invariance. Lagrangian formalism is not. But if you want to talk about energies, then you have to specify a frame, because Hamiltonian is conjugate to time. And if you start mixing time with other directions by making Lorentz transformations, then you are in trouble with this notion of energy, with notion of the Hamiltonian.
Yes, but what I think is that the energy of a particle should be a scalar, and if we consider only spatial rotation, it should not change. But why?
If your particle, again, you answer your question yourself. If particle is a scalar, you answered yourself.
I mean, the energy of a particle is a scalar, I think. It have no direction, it's just a quantity, and if we just rotate our reference frame, it should not change.
It depends what you call by energy. Here, I prefer not to talk about energy. Here, I prefer to talk about eigenstates of the eigenvalues of the first quantized Hamiltonian. Now, of course, what I mean is that energy itself, the Hamiltonian undergoes a transformation. So H on P goes to H on RP, for instance, under rotations. But if you look for the eigenvalue E on P, the eigenvalue is square root of P squared C squared plus M squared C4. And that is, of course, invariant, no?
Okay, I see. So the operator changes, but the
operator changes. Operator, that's what I mean by change of the Hamiltonian. Operator changes, but E on P depends on P in a way as it should depend for a relativistic point-like particle. And that is, of course, invariant because it depends on P squared.
Yes.
Now, for the scalar field, the Hamiltonian itself depends on P squared. And therefore, we never see any problem with this. We see that Hamiltonian is invariant and energy is invariant. For the Dirac equation, the situation is different. Hamiltonian is a matrix operator in the first quantized theory. It's not invariant. But eigenvalue still is the same as for relativistic particle, and therefore it is invariant. With helicity, the situation is different. That's why I insisted on talking about helicity in first turn, because here, this is an explicit form of helicity operator from where you see that this guy does depend on the momentum itself, on the components of the momentum, and it might change the sign when you change the frame.
Yes.
Okay.
Professor,
Yeah.
I have a question. Like for as you said that for a scalar field, the energy is invariant, right?
Mm-hmm. Yeah.
In another frame if we go.
Yeah.
So, but yeah, from the expression, okay, this is saying that these two energies would be equal. But for example, like if a scalar particle is moving in one field, and suppose we see the scalar particle from a different point of frame, for frame of reference, in one direction.
But no, so you should be careful here. Energy is not changing under rotations of momentum. Eigenvalue is not changing under rotations. But if you would be doing Lorentz boosts, then this is a different story.
So there it should change, right?
But there you destroy everything. You destroy your Hamiltonian. You boost yourself. You see how to describe it. For instance, I mean, this is more or less obvious because you boost yourself with respect to an object. Therefore, in your frame, your object starts moving, so it gets extra energy.
Right.
That should not be too much surprise. If you just rotate yourself, rotate the frame, this does not happen. But if you boost, if you move, you start moving with a certain velocity, then of course, yes, the object gets energy and may produce a work on you.
May produce what?
A work, it can work on you. No, for
Oh,
instance,
yeah.
if you have, I don't know, a ball and the ball is not moving and it's fine, but if its ball is moving on you and hit you, because you are running against the ball, that means that you are going to another frame where you boost your object. Then you can meet it, and then yes, the ball will act on you.
So this is for the case
ball
when
or stone or whatever. Yeah.
So this is for the case that we are located in one point and we are seeing the field, right? The total energy, which is
Yeah,
constant.
in this case, you can talk about energy of a wave or energy of a particle. Yes.
So and this is obvious also. We are looking from one direction and seeing the total energy to be constant.
Right. So object transforms from frame to frame, from one Lorentz frame to another from Lorentz frame in a certain way. And accordingly, you have to ask about what happens to your observables, how they do depend on the Lorentz frame, those quantities which you want to measure, how they do depend on the Lorentz frame. What are you trying to measure, actually? So in this case, we are talking about measuring energy. Energy, we know what is this. So energy is, say, eigenstate of our Hamiltonian. But when we talk about the Hamiltonian itself, this means that we fix a certain Lorentz frame. We fix a direction of time. In the Hamiltonian formalism, we have to fix the direction of time, because Hamiltonian is a generator with respect to the shifts in time.
And that's why we are doing three momentum integral, right?
Yeah, in a way, yes. In a way, we are solving not directly the eigenvalue problem, but what we are doing, we are solving the Dirac equation, which is a time-dependent equation. Right? It involves explicitly time. Time is in it.
Yes.
So there is a difference. When we talk about equation, we know the only thing which we want to require from the Dirac equation is its Lorentz covariance. So we put this principle of Lorentz covariance as a basic principle, as a fundamental principle. It's called Einstein relativity principle. It means that laws of physics must look in the same way in any Lorentz frame. And once we fix the frame, then we can develop the Hamiltonian formalism. We can say, well, there is a time direction. With respect to this time direction, we construct the generator of shifts in this time direction, and we get our Hamiltonian as a generator of shifts in the time direction. Now, in general, if you start performing Lorentz transformation, your Hamiltonian will not be invariant because of mixing of time with other directions.
So,
But this is what is expected. Lorentz Hamiltonian formalism always breaks Lorentz invariance.
yes.
This is one of the unpleasant features of the Hamiltonian formalism. It's good for canonical quantization, but unfortunately, Lorentz invariance then is something which should be then a posteriori checked upon the quantization is done in the Hamiltonian setting. Okay, that is how things are looking here.
So we have means we have considered a special case. So we can construct a general case also. And for that, if we consider V to be 0, then our whole formula and expressions will be similar to this as we got.
What do you mean by V? V?
So we are not moving, we are stationary, but we can make a general expression, right? If we are moving. So this is the special case for V equal to 0.
Yeah, so we are in a frame. With respect to us, our particle moves with a fixed momentum P. So we have momentum P, which describes our particle.
And what about if it's accelerating?
Sorry. So what do you say?
And what about if it's accelerating?
For particle to accelerate, here you need a force. That means that you need an interaction term with other particles or with the external field in such a way that the momentum will not be conserved anymore. But in our case, we know that momentum here is conserved, right?
Yes. Okay, so we need to add an extra term, like Yukawa force we added in scalar field.
Exactly. We need to add something which will lead to the effect of acceleration. So our particle, our Dirac particle so far is what is called free particle. We are describing so far free particle. Free particle, and we choose a certain inertial frame, like we do in mechanics. Say standard way, we choose usually an inertial frame. In an inertial frame, we describe our physics. Of course, we can pass to the non-inertial frame, to a non-inertial frame if we wish, but this will only complicate things, so we never do that in reality.
And because of interaction, right, you have some things also changing, right? The number density or something.
No, once again, what we are describing here is a free particle. So free particle, okay?
Yes.
If we want to describe interactions, what we will do in particular in the second part of this course, then we have to modify our equation. We have to do something. For instance, we can introduce an interaction of our particle with an external field, like we did when we derive Yukawa force. Or we can add a term which describes self-interaction of a particle. So particle field acting on itself, like for instance, phi-4 term in the phi-4 theory of a scalar field. But we have to change something. So far, our particle behaves itself as free.
Yes.
And what we are, what means free? It's free. It's the fact that it is free. You see from this standard relativistic dispersion relation we are getting for our wave or for our particle, for our spinor, which describes now.
Or we can say we can
Two
also
kind
say.
of. Yeah.
Or we can also say like this, that this is the equation for a particle moving in high energy, right? Then you get you can neglect those small interaction terms.
No, this is in a way sometimes also possible to say yes, that interaction terms are negligible. No, at certain approximation, yes. This we are considering a situation of particles which is isolated from anything else. It moves by itself somewhere in the universe, very far away from any other particles and any stars and whatever. Asymptotic situation where it's isolated from anything in the universe.
Right.
But we need an equation. We need to understand how this particle behaves itself. What is this motion? How this motion looks like? What is this? As soon as we know how to describe free motion, then we can take into account interaction terms. But first, we need to understand free particles. And free particle is essentially defined by the way, by one thing, is how this object behaves itself when you change the Lorentz frame. And how it behaves with respect to the change of the Lorentz frame classifies then our particle objects like spinors, scalars, vectors, and so on. And correspondingly, we write an equation for this particle which takes into account the fact how particle transforms under the inertial frame. And our equations take this into account. Either this is scalar equation, Klein-Gordon equation, or this is Dirac equation, or for electromagnetic field, it will be Maxwell equations. Okay?
Yes.
That's an idea. And of course, the next step, a very non-trivial step, would be to take into account interactions, because we are living in the interacting world.
Yeah.
Sure.
Real world scenario.
Yeah. Okay, so what do we do? I think we continue. So next time we have our last lecture, right? And our next lecture is the last one in this semester. No, and then I come to the charge conjugation. So I will explain the concept of antiparticles and charge conjugation. And I will, if I will have time, I will talk about canonical quantization of the Dirac field. Actually, we prepared everything for this, for doing this. And if I will not have time, then I will continue with this in the next semester. Okay, but for today, that is all. If you have any questions, further questions. If not, then I wish you a very pleasant day, and we hear each other next Friday.